I love the question about why don't we just use MPI, because this part of the talk is going to be about like making people who don't want to touch MPI happy. So this as was previously talked about, Julia comes with an already native distributed computing support, and so I've been working with that at NERSC for a while. So I work in the data science engagement group at NERSC, which is a group that actually focuses on helping users with data-intensive workflows. So not necessarily traditional compute and simulation workflows, but analyzing data from instruments, for example. And so maybe I should also say, NERSC, what is NERSC? We previously heard about OLCF. That is a leadership computing facility. Their job is to try and get the biggest kind of jobs, the biggest compute available on the planet to work. We are the mission compute facility for the United States Department of Energy Office of Science. And that means we take everyone else. When you are funded by the Department of Energy, you can request compute hours, and this is a decision that's not made by us, but by our program managers, and they will send you to NERSC. So that means that the workflows that are running on our systems, they are cross-cutting across pretty much all of the scientific domains. We have about 9,000 active users. They are distributed across about 1,000 projects. And these users are globally distributed as well. What I really like to point out here, though, is most of our users, about 59%, are from academic institutions. So we are not solely a government agency. We cater mostly to academics. And the thing that I really like is this part down here. If you add up postdocs, grad students, and undergraduate students, you get more than 50%. So most of our users are actually early career scientists. This might be a reflection of the fact that most of the work is done by the postdoc and not by the professor. But it also means that it's a very young user group. All right, so if you were to pop open a cabinet of so we currently have one production supercomputer. Cori, which was our outgoing machine, has been decommissioned. In case you were still a Cori user, you've lost your data on Scratch. So we are running Perlmutter now. So if you popped open one of those cabinets, what you would see is a fairly sophisticated chassis to manage power and cooling. But essentially what you care about is we have two kinds of nodes, a CPU node and a GPU node. If a GPU node has 4 A100, so NVIDIA A100 GPUs, and one AMD Milan CPU. Crucially, it has 4 NICs, or network interconnect controllers, interface controllers, sorry. This will be important later in this talk. Whereas a CPU node has 2 AMD Milan CPUs, but only 1 NIC. So just to summarize what I was just talking about, most of our users at NERSC are non-HPC experts. So, and it's important, we can't force them to become HPC experts. We can't say, well, if you don't learn HPC, you can't use our systems. And additionally, the workflows that are running on our systems are incredibly varied. So we have to provide a wide range of capabilities, and that's already reflected by the fact that we have 2 different nodes, right? And so the challenge for a package like Distributed is that it needs to, essentially needs to, out of the box, know the right thing to do. So this is something that I've been thinking of for a while. It's actually something that Valentin, a thought that Valentin initiated. So Valentin, you get credit if this is terrible. No, I hope it's not terrible. No, the idea is we need to rethink about how Distributed actually talks to the resources that it needs to use. And so I want to start with a workflow support story. A while ago, about a year ago, I got a ticket that said, Perlmutter is about 100 times slower than our university cluster. And of course, you're like, oh boy, what the hell's going on there? And so the user then produced this small minimal reproducer, and it actually represents what you see a lot in terms of these non-MPI HPC workflows. It's some sort of, here, this is not Dagger. I told them later to use Dagger, by the way. But so you have some, you configure some cluster manager. And here what you actually do is you use srun to start a pool of workers. You wait for the workers to start. And then once they've all started, you run this little benchmark that essentially this is intended to stress test the communication by copying this random data for several iterations, in this case, 20 iterations. The reason why you might care about this is because imagine you have a sophisticated workflow that's making decisions and you want to start additional workers, right? So you should be using Dagger, but at the time, the user was using this. And by the way, Dagger uses distributed under the hood, so all of this is still relevant. And so what we found is, just by thinking about how much data we're transferring, we were way too slow, and the scaling was horrible. So ignore the red blocks here. The blue blocks are sort of by what happens by default. So as you scale from 2 to 20 workers distributed over 2 nodes, your time in the loop is just becoming, this is the per loop iteration time, by the way. So it's big, it's a problem. So we started digging around and we found the problem. The problem is, and the way I found the problem, by the way, was that the admin sent me a Slack message saying, you're spamming the node management network. It's destabilizing the cluster. Stop it, please. And that's really what ended up happening. Our management network interface is the lowest number network interface on the nodes, and Socket by default just grabs that. So we were dumping all of our data across really normal Ethernet. And so after discussing with the admin, they said, well, it's easy. The fix is easy. Just put this in your startup.jl and tell every user to do that. Now, this actually doesn't solve the problem, I think. And there's 2 reasons. The first one is users don't read documentation. So even if you put this up in big red warnings, people will, even if they're good intentioned, will miss this. And so the effect that I like to show is, so you have a lot of good intentioned users, and they're all trying to get onto this log here. And they all want the system to be stable, but it's actually okay. The Wi-Fi isn't good enough, but basically these turtles are destabilizing the log. Eventually they all fall down. Anyway, so So the other reason what this doesn't fix is if you look at one of our GPU nodes, you see you have these 4 NICs here, and that snippet there essentially just picks H's and 0. So it picks this NIC over here and ignores the rest. And you can't actually just say, oh, well, then I'll create a more sophisticated script. Well, it gets very sophisticated because we have different kinds of nodes and they have different configurations, right? So you then have to start looking up host names and things like that. That's kind of nasty. So instead, this is what we were working on. The first step is, well, we've got HWLock. How about just using that to tell me which NIC is closest? Sounded like a simple idea. Turns out that it required quite a lot of additions to HWLock to get the PCI interfaces to work properly. But that works now, so yay. And then use the distance on the HWLock tree to find out which NIC is closest to what core. And then, so this is effectively done. This is edge cases are still a problem, but that's okay. And here is a conversation we still have to have. How do we integrate that with Distributed.jl? And just to demonstrate how it works, if you use HWLock and just print the tree for a GPU node, this is highly truncated. It's like 10 pages long. there's USB ports. I didn't know, but I saw USB ports. Anyway, the point is though, you have, when you truncate out all the stuff that you don't need, you see a NUMA node, and then you will see a host bridge and PCI bridges, either to the HSN or the management network, and you can see the different HSN interfaces here. And so what we want to do is we want to map these to different processes, depending on where the process is running. And so, so this is just showing how it actually works in the library. So basically, for each process, we can compute the distance, and we say, well, we want this one. This is the one we bind to, okay? And this is actually what those red bars are about. So when you then run this with thread binding to cores, it works great. There's no problem anymore. In theory, at least. And so it does still, there's a caveat here though. So the way that this is architected is this package here, which is still a bit experimental, handles the mapping. And then it also at the moment handles some machine-specific configuration. And we have to kind of think about how to best support that. And so that brings me to my to-dos. Essentially, this is pre-alpha, but we want to make it alpha and beta very soon. So if you are interested in discussing what, especially this question about how this gets integrated with distributed, please discuss. We can have beer or not beer. And if you also want to try things out, let me know. So any questions? I answered all the questions. Excellent. Oh.
Thank you. So I guess the question is, I mean, maybe this is, how do you have any ideas on how it should integrate with distributed? I mean, distributed is a bit of a, it's been around for a long time.
Right.
There's a lot of some funny interfaces in there for anyone who's ever delved into it. Artisanal, that's an extra word. Yeah. Do you have any thoughts?
This is my opinion, of course, and I don't want to devalue anyone else's opinion. I think what we are aiming for, what I would want to aim for, is something that works as seamless as possible for the user. So that should be the constraint, and then within that constraint, I would like to minimize the amount of dependencies that this introduces. So one example could be that if HWLock isn't installed, then just don't use it. It sort of creates a little bit of an edge case where it might just be like, so the plan that I currently have, and people are welcome to give feedback on that, is a preferences file that the sysadmin puts in a global path, and if it requires binding to the cores, then it looks, do I have HWLock? Can I run this? If not, here's an error message and force the user to add it. That would be one way. And if it's just on your laptop or so on, you don't really need HWLock. Behind you.
Hey, so I heard a little bit about pinning to cores. So are you planning to have integrations with thread pinning, .jl? I believe that's the name of the package. Or are you planning to do this kind of more just from the low level? How is that going to work?
So basically, what if you don't use thread pinning and your processes hop around, then, well, you still get the speed up of having the high-speed network, but then, of course, you don't have the NUMA locality, right? It's always good practice to use thread pinning, at least for the stuff that I do and the stuff that I've seen. So, but it's not going to be a requirement, no.
Yeah, okay. I have another question. Oh,
sorry,
don't have
just
time.
1 second before you pose the question, since mapping was mentioned, just one more comment. The question also, there's dependency as well, right? Like I mentioned, I use currently LS CPU as a backend. I could use HWLock, would be fine, just a bit of work. but it's still a dependency, right? So you would have to know about the system if you want to schedule on a system, right? So, and not everyone is willing to add this. We also have the discussion with Julia Base, by the way, whether we should spawn the number of threads per default according to the core, so CPU threads or whatever. And to figure that out, you have to have a dependency, and not everyone is willing to have that. Sorry, pose your question.
Okay.
Oh.
Yeah. 1 second.
I was taking a look at your GitHub page for HWLog.
Okay.
But like, is it possible to use InfiniBand with this kind of setup?
I don't know.
Because it's cited here, like, it also gathers various system attributes such as cache memory information.
Right. So HWLog does find InfiniBand devices, right? But I thought you were referring to distributed. I don't know if
So
right.
can I use distributed?
I don't know if distributed can. It's
Distributed.jl just uses TCP/IP, and if you want to get anything faster, MPI, or if you're looking for a fun project, reach out to me and we can talk about UCX.
+1 on the UCX part.
Yes. Also, UCX does these adapter selection automatically.
I think
All right, so let's
next
thank Johannes again.